Okay, YouTube, in this video we're going to quickly review how to graph linear equations as a warm-up for solving systems of equations. And so the instructions here ask us to graph these linear equations that are either written in slope-intercept form or standard form. And that's kind of the ideas that we want to review here. And so in terms of slope-intercept form and standard form, okay, these are often how equations of linear equations are written. And we use these so often that we recognize patterns that are involved with them. So we're going to say slope-intercept form. This is this y equals mx plus b. And the reason why is because we have m is our slope. Remember that slope is our rise to run ratio. So rise over run is our slope. And then b, this is our what we're going to call our y-intercept here. Okay. And then with respect to standard form, we're going to look at standard form things also, but I'm going to write this just for now as ax plus by equals c, where we're going to say all variables on the left-hand side, and then all constants on the right-hand side, So let's go ahead and get started with our slope-intercept form. This very first equation right here, you'll notice that this is in y equals mx plus b form. And one easy way to tell that it's in slope-intercept form is that y is isolated. That is, we've solved for y. And so if it's a linear equation, we can tell both the slope and the y-intercept for this. But let's just recall really quickly here what it is that we're graphing. What we are graphing when we graph any equation is a series of points that when we plug them back into the original equation make it true. And so often when we graph things in slope-intercept form, I guess when we learn how to do it, we come up with this t-chart where we just plug in random x values and come up with y values. So a few things I want you to see. First of all is if it's in slope-intercept form, this y equals mx plus b form, if you were to plug in 0 for x right now, we would get y equals m times 0 minus b, or in other words, we would just get the negative b value right there. And so we refer to this as the y-intercept just because when you plug in 0, well, that's what's going to be the y value on the y-axis. And so we would say if we had the equation y equals 2x minus 1, then to plug in 0 for x would just give us negative 1 here for our y-intercept. So negative 1. If we plug in 1, we would get y equals 2 times 1 minus 1. In other words, 2 minus 1 is 1. And then y equals 2 times 2 minus 1, or it'd be 4 minus 1 is 3. You can see that really these values here, at least on this line, are going up by 2 every time. And this is just a consequence of the slope. And we can see that easily here the slope is 2. And so to go backwards, we'd go down by 2s. We say negative 3 and negative 5. But essentially, to graph this line right here, if it's in slope-intercept form, then our method is always going to be to just identify the slope and the y-intercept. So in this case, our slope is 2, or I'm going to say 2 over 1, and then I'm going to say our y-intercept is negative 1. And so we can go graph all these points on this line that are solutions, but essentially what we could also do is just say that, hey, it hits the y-axis at negative 1. So we're going to go down to 0, negative 1, which is this y-intercept point right here. And then we're going to say, using our slope, which is 2 over 1, or rise over run, we're going to rise 2 and run 1. We say that this point also has to be on the line. You can see that the point 1, 1 is certainly on this line. And if we were to rise another 2 and run another 1, you can see that this is the point 2, 3. And so this is our 2, 3 solution pair. And so I'm going to put a few more points on here if I go down 2, back 1. And we're going to say that this is the set of all solutions to this equation right here. And so what we want to do is make sure that we label this y equals 2x minus 1. So slope-intercept form, one is graph the y-intercept first, and then use the slope to find all the rest of the points on this line. Now, if it's in standard form, what we're going to use is the intercept method to graph. So intercept method. Now, one thing I want to mention here is this. We're going to basically find where it hits the x and y axis by finding the intercepts of the graph. And so if it's in standard form, where our variables are on the left-hand side like this would be an equation like 2x minus 3y equals 6. And this is this equation that I have up here. Essentially, when we have a line, any line that is, say, I guess not on an axis like this, it's going to hit the y-axis, it's going to hit the x-axis maybe somewhere. But the point here I'm trying to drive home is that basically the y-intercept has to have an x value of 0, and the x-intercept, whatever that is, has to have a y value of 0. And so what we're going to do is basically plug in 0 for x and solve for y, and then plug in 0 for y and solve for x, and then once we have those 2 points, we can just connect them and have all the other points on the line. And so with this equation that we have here, if we were to plug in 0 for x, we would get 2 times 0 minus 3y equals 6. You can see pretty quickly that this term, the x term, just drops out when you plug in 0 for x. And we just get left with negative 3y equals 6, which would imply that y equals negative 2 if x is equal to 0. And likewise, if we were to say, well, now looking at the same equation, if you plug in 0 for y, then this term would drop out. We would get 2x minus 3 times 0 equals 6. In other words, 2x equals 6 if x equals 3, and x equals 3 if and only if y equals 0. So for this line right here, we would just go on our x-axis. We would say the x-intercept is 3, and the y-intercept was -2. So just looking at this equation, we could have said, hey, plug in 0 for x, get y, plug in 0 for y, get x. And then what we'll do is we'll just connect the dots here. So we'd say that this is our equation here, 2x minus 3y equals 6. And these are all of the pairs of x's and y's that make this true. Now for our last two here, essentially x equals 4, one thing that I want to point out here is this. The only way that you can ever make this equation true is if every single x value of every point is 4. So that means that this could be a -2, a -1, a 0, 1, a 2. Weird. Y can be whatever it wants because there is no y in this equation. So to graph x equals 4 and all of these points here, this would be like 4, -2, 4, -1, 4, 0, 4, 1, 4, 2. You can see that really all we're doing is we're graphing a vertical line. And this would be the vertical line having all x values equal to 4, whereas now looking at letter D, we can say letter D, what would make this equation true? Well, the only thing that's going to make it true is if we have y values that are equal to -3 when we put it back into our original equation. So this could be like -2, -1, 0, 1, and 2. But one thing we want to keep in mind is that when we graph these, we would say 0, -3, 1, -3, 2, -3, -1, -3, -2, -3. That when we graph a y equals a constant equation, then we're graphing a horizontal line. Whoops, -3 here, but a horizontal line through that y value. Cheers.